I'm very pleased to present a new contributor to the Inductica project, Chantal Roth. Chantal has her PhD from ETH Zurich in Switzerland in scientific computing. Incidentally, that is the same university Einstein went to. She works primarily in the biotech industry developing algorithms, but she works also as an independent researcher who has put together an integrated hypothesis of how the ether works. Today's video will be the first in a many-part series titled The Mechanical Universe. In this series, Chantal will explain how modeling the ether as an elastic solid could explain many physical phenomena: time dilation, length contraction, matter waves, gravitation, electromagnetic forces, and many more. What most impresses me about Chantal's work is that it is an impressive step forward in understanding how all physical phenomena we see around us could be constituted of the waving of a single unified medium. Let's hear Chantal's first lecture detailing her mechanical universe here on Inductica.
There are quite a few concepts in physics where we really have no idea how they work exactly. For instance, we know how cars work, right? We have models, we can simulate it. But what about when I ask, why is the speed of light constant? So normally the answer is something like, well, it's just a postulate. There's no mechanism. And when we ask, why does time slow down when we move fast? Well, it's just because of the above, right? Again, because of the postulate. There's not really any explanation. And for instance, how does a magnet work? How does this attractive force work when I have two magnets? Normally, we are told something like it's because of some virtual photons that are exchanged. But how does that work? How can you have virtual photons cause an attraction? And what are photons, by the way? And why are they virtual? So there's really no explanation. So I want to know how things work, just like we know how a car works. And it's probably pretty clear also with quantum mechanics. I mean, we have all these interpretations, and it seems like people do want to understand because that's probably why we have all these interpretations. But none of them really explain anything. The one exception is probably the pilot wave theory, which does attempt to explain that there's this wave function which is real, which controls the movement of the particle, but it doesn't explain what the wave function really is, what that wave is made of, and what is the particle. So, and normally we are told, well, there are no deeper explanations. We have to just accept it. And I don't like that. And also, I don't believe we need any magic to explain this. So this is the starting point of this whole series. I simply want to understand how physics works and why. And really important, without any magical ingredients. So I don't want to have to add extra dimensions or any faster than light things or time reversals. I want to keep it as simple as possible, a simple mechanical model that still explains, hopefully, everything, and it doesn't contradict the current observations. Just like with a car, where we can actually simulate what's happening and understand the mechanics. So during our journey, we will address a lot of different questions that have been bothering me. For instance, how can we turn light into matter? Or what is spinning in spin 1/2 exactly? And what is charge? Is there anything physical or is it fundamental? Can we resolve the wave-particle duality? What is a photon? I know this sounds pretty crazy, and you might be wondering, is this some new crazy theory of everything, or what is that? Well, actually, the ideas are not new. They are already known, and they're surprisingly simple. Various people have worked on this, on different aspects one way or another. Some pieces are hidden in papers, others have been forgotten or just overlooked. And of course, over the course of this, I have been having a lot of conversations with various people, and all of this has helped to move this ahead and, get the thinking process started. And so my contribution really is that I'm trying to put all these pieces together into one coherent, consistent, logical picture. And also, I've been writing a lot of computer simulations because it's really easy, at least for me, to get lost in the math. And, it's so easy to make mistakes. And some concepts are really hard to understand. And so I really write these simulations. I wrote them mostly for myself so I could understand everything.
Hmm.
And it just helps, I think, if you can play around with this to really get an intuitive sense of how this works. And all these simulations are freely available. You can copy them, you can change them, you can use them, or even better, maybe create new ones and share them as well. And we'll go through many of them in this series.
And that link will be provided to everyone in the video
Oh,
description,
yeah,
by the way.
absolutely.
So if
Yes,
you want
yes,
to, so you can click on that in the video
exactly.
description.
Yeah, yeah. And if anything's missing, let me know. So, of course, this covers a lot of topics, and there's just absolutely no way to cover this in a talk. I mean, I've tried, but it's just 1 hour is not enough, obviously. So I thought we should do this, step by step, focus on one concept at a time. And you might be wondering, why am I doing this? Well, my goal really is to motivate people to think about this, to debate it, and to get people to hopefully also participate, right? Because each discussion leads to a new idea, and hopefully all together we can figure this out one day. And so to get started, the first topic will be, it's a very simple sounding one, properties of space. And by the way, thanks very much, James, for being my listener, so I don't have to talk to myself.
Yeah, yeah. It never occurred to me that some people are, uncomfortable talking to themselves, because I do it all the time. And then, like, that's how I shoot my videos. So I'm very happy to be an audience to maintain your the normal psychology that you possess.
Thanks. Yeah, that's good. Okay, that's it for the introduction, and now we can move on to the next. Okay, so in this first episode, we will be discussing the properties of space. Now, what do I mean with that? We have all seen images like this where, space-time is pictured as this sort of fabric that's bending and, it's curved. And then somehow Earth is able to curve this. And on the other hand, also the curvature controls how the Earth is moving. And when we ask about, well, what is this grid really? We are told, well, it's fundamentally, it's just geometry, it's just mathematics. There's nothing there. It doesn't consist of anything. There's nothing there. So it's not real. We are told it's abstract. So
Hmm.
also when we ask what is space-time, again, we are told it's abstract. It's just math. And so when we ask, well, how does general relativity work? We have the field equations and we can do all these great calculations, but there's no mechanism explained how this works. So here's a simplified form of the Einstein's field equations. And basically we have the mass energy content, which basically says how is the energy distributed in a volume. And then we have this results in curvature. But the problem I have is, and I actually have a simulation for this. Let me just start that real quick. So the problem with that is we know Earth is real, obviously masses are real, and the movement is real, but the curvature is supposed to be not real. That to me causes a logical problem. How can something that's not real affect something real? And I have a problem with such logical inconsistencies, right?
Just so
Yeah.
you know, well, like not everyone thinks of space-time as not real or merely an abstraction.
Mm,
But I think that's the default position of most people who work in this field because they've
yeah,
rejected philosophy.
exactly. Yeah, yeah.
They've just reject and really what they've done is reject physics because they're refusing to ask what is the physical nature of this thing. They're refusing to answer fundamental questions about what this stuff is that's affecting the trajectory of matter and light. Um, but there are indeed philosophers of physics who do think about this,
Yeah.
but in my view, for the most part like very far off. In my view, the way to think about this is that because this is something that can act on entities and
Mhm.
something that can be acted upon by the entities
Yeah,
nearby,
yeah.
it's an entity. So
Yeah, exactly.
personally, I
Yeah.
know I know in the PAMO we don't all agree on this, but I have strong reasons to believe that we should not refer to this as space. We should refer to it as an ether or a plenum, which emphasizes the fact that it is an entity. I don't want to, steal your thunder in your presentation, but that's my
Yeah, I'll
philosophical
talk about
stance.
this too because there's some fear of people to use that word. And so
Yes.
I'm not going to call it that. I'm going to try to explain what I mean with that. And then, if some people like to use the word ether, it's fine, but there's always a misconception. Um,
Right.
so
We do
so
need to clarify what we
oh,
mean. I
absolutely,
mean, I'll just say
absolutely.
what I mean by an ether is I just mean I'm not committing myself to anything that may have been committed to in the past with that word. I'm just
Yes,
saying
that's really
it's a
important.
thing that can act and it can be acted upon. It's
Yeah.
an entity of some
Yes.
kind at each location. And you're kind of noting the alternative is madness. The alternative is, well, if it's not an entity, what is it? Is it pure action? Is it just an abstraction? All of this gets into a very dubious view of reality.
Exactly. Yeah.
So, I mean, well, it's more than dubious. It's false. It's demonstrably false philosophically. But we won't
Yeah.
get into
Yeah, I
that
agree.
today
Mhm.
since we're focused on you actually solving or, putting a first step towards actually solving the problem, using this
Trying
better
to,
philosophical
yes.
perspective
Of
to
course, by the
solve the
way,
problem.
I might be totally wrong, and that's totally fine with me. I just want to figure out how it works. And if people find
Yeah.
a reason to say it's wrong, that's okay with me. You know,
Right.
so,
If
but
someone were to disagree and say, "No, it isn't like this. It's not like X. It's like Y." Well, then congratulations because you're agreeing at least implicitly with our mission here, which is to
yeah,
find the
exactly. Yeah.
entities behind this. And if you don't think these are the real entities, like we're on board with you. This is just a hypothesis.
Yes,
So,
yes.
yeah.
So let's see what Einstein said about this. He's a smart guy, and people usually agree with what he says and will consider it at least. So he said in 1920 that according to the general theory of relativity, space is endowed with physical qualities. And that's really the one thing I want to highlight. And in this sense, therefore, there exists an ether. Now we can debate the word ether, but the point is he agreed that space needs to have physical qualities. So according to the general theory of relativity, a space without ether or without these physical qualities is really unthinkable because in such space there would not only be no propagation of light, but also no possibility of existence for standards of space and time, measuring rods and clocks, nor therefore any space-time intervals in the physical sense. Now, I know right away people will object. I've had these conversations. Well, but Michelson-Morley proved that there's no ether. Okay, we'll explain that in literally a minute. Okay. Speed of light is constant for everyone. Yes, it is, and we can show that is correct. We will explain this in detail. So there's so far no contradiction. Now, I know this is a bit premature because we'll talk about this a lot later again, but because like most conversations stop here, I thought I should probably start with the Michelson-Morley experiment, at least explain it a little bit. So the idea is this, right? We have this light source that's sending on photons, and there's a beam splitter, and the light is sent to both two arms that are equal length, M1 and M2. And then there's a detector. So now when the whole apparatus is at rest, and if the arms are the same length, you can see these colored balls, which are, the photons, they arrive at the same time here. See?
Hmm.
And when we look at the interference, well, there's no interference because, there's that one arm has like the red wave and the other one has the blue one. They arrive at the same time. There's no interference pattern at all. So now, when people thought about the ether early on, like when they had this idea,
Real quick, why is there no interference in this situation? Because they're different colors, is what you're saying?
oh, I mean the color of that ball here is supposed to be like the wave. You can imagine the light wave. So
Yeah,
um,
maybe it's a pulse.
a pulse.
They
Yeah, yeah. I can
emanate just
probably
a
make it
quick pulse,
slower.
maybe.
Yeah, yeah. It's a pulse. But see those dots. They arrive at the same time. So these two dots here, they
Yep.
arrive at the same time. So when you have the red wave and the blue one, they arrive at the same time. Th- so so let's see what happens. Let's see what happens when we start to move the apparatus. And let's say there's no length contraction. At that time, the thing is when they did the experiment, they didn't know about length contraction yet.
Yeah.
They didn't consider that. So let's move the apparatus and you have some wind. This is sort of ether wind, okay?
Uh-huh.
When we start to move it, we can now see
Mm.
the shifting. So now when you look at this, let me turn up the speed of the wave a little bit so it's a little faster. You can now see because the light, one of the light waves is done, you can see the speed, right? To the right is
Yep.
slower.
Yep.
And it comes back, it's faster because, well, it has to fight against that ether wind, basically, right?
Yeah.
And now you can see these balls, these photons are no longer arriving at the same time, right?
Mm.
And even the tiniest shift, if you do it clever setup, you could detect that change in interference. You can see that in the detector, you can see that interference pattern changes.
Yeah, I see. So earlier we saw only one wave. Now we're seeing two. But the reason we saw one wave earlier is because the two waves were just overlapping with one another perfectly.
Yeah, it's easier to do.
And that's
Yeah,
and that's
when I enable the
consistent with the
sum,
balls arriving at exactly the same time.
and you can see that
And now,
when I
yeah.
do the sum, right? So let's see when we everything is rest, they add up. You have this nice wave. When we speed it up, we start to see, you know, the interference, right? It changes
Yeah.
you can see that.
Yeah,
So
so the
of course,
white being the sum and
yeah,
the white
exactly.
is now attenuated by the fact that these waves are canceling each other based on the fact that they're no longer arriving simultaneously.
Exactly. Yeah, that's the
Yeah.
thing. And now what happened? They saw nothing. No interference. Nothing. Okay. It always looked like this. Always looked like this. And they're like, oh my God, we just proved there's no ether. Oh my God. The thing is, what they didn't know is that there's also length contraction. So now when we enable length contraction, okay, that means the arm, if you can see it, when I move fast, this arm here will contract in the length.
Hmm.
Um, and now it contracts just by the same amount as we have the impact of the light wave. And now they arrive again at the same time.
Yep. So we see here that the arms are different lengths. Why? Because one is going into the ether wind. And so
Yes.
this is a visualization of the Lorentz
Yeah. Of
view
course, this is
that
this
like
is like a
if
cartoon
you
version, but yeah, just to illustrate,
yeah, and
yeah.
so even so what's interesting is that even though the ball going upwind is going slower, you can see, and then when it goes downwind, it goes faster. Normally that causes a difference in arrival at the detector, but because of the change in the length of the M2 arm, they now arrive at the same time, just like
I know.
it does when there is no ether wind.
Yeah, exactly. So, in summary, they made some assumptions when they created this experiment. They thought that Earth was moving through the ether. They thought the arms will remain fixed. They did not consider length contraction.
Yep.
And that's why the null result, it's called, is expected. So this proves nothing. It just proves that you got to have length contraction, right? And it's funny because this was done in 1887, and the Fitzgerald and Henrik Lawrence, they later independently developed the idea of length contraction, but it came after. But people don't know this. They always say, oh, it's been disproven, like objection right away, right?
Yeah.
So I hope people will agree that it makes sense to continue to say, well, let's see what happens when we, you know, consider that maybe space does have properties. Now, what do we know about real materials? And again, I can see the objection already, but again, let's look at real materials first. How does the speed of a wave behave in a real solid, for instance? Now, here are some examples. And basically, the shear wave, so the transverse wave, depends on the shear modulus. That's how stiff something is. So, like a soft rubber has less stiffness than diamond, for instance, and depends on the density. So, the denser something is, the slower the shear wave. There's also another formula used, but I'll focus most on the first one because it's more easy to understand. So let me just open that one real quick. So here I plotted this. These are different materials. On the x-axis, we have the density, and on the y-axis, we have the stiffness. And now we can see when we calculate, because we want to get the speed of light, right? So let me just zoom out a little bit. So here's the speed of light. And so we can ask the question, well, what kind of properties would space need to have to support the speed of light that we know. So for instance, if it had the density of air, then it would, well, it's still gonna be quite a bit, about a million times or so stiffer than diamond, but it's not too
Hmm.
extreme. So you could imagine this is something, I mean, we don't know, right? We have no idea what the density is, but we can figure out if we knew the density, we could calculate the stiffness. It has to be on this one line here, basically.
Hmm.
So here are other materials, titanium, steel, graphene. I
Hmm.
didn't know graphene had such a high speed.
Yeah, that's interesting.
Rubber, so just to get
A lot of people use this as an argument against the existence of an ether because they basically say, look, I mean, they would produce a graph like this
Mhm.
and they would say, I mean, I've certainly heard this as an argument against the ether. They say the properties of an ether material would clearly have to be insane. Why? Because it would have to be extremely stiff while at the same time very rare, very not
Oh,
dense.
yeah, absolutely. Yeah, absolutely.
So,
So, yeah.
but my personal challenge to this is well, we already are not committing ourselves to the idea that the ether is some kind of substance, as has been found in the past, such as diamond or graphene or
Oh, no.
carbon or
Yeah, yeah.
any.
I want to be clear. I'm not proposing. That's why I'm saying the space has these properties, right? I'm not even saying it's a material. It's obviously not
Yeah.
made of atoms. It's not like a diamond. It's not like rubber because it doesn't contain, protons. No, no, no. So we can just call it space itself. That could be a whole other discussion, but it has property. The properties need to be such that if it were a material, it would have to, based on the materials we know, these are the properties it would have, basically.
Right. Now, I have a question. What would stiffness and density mean in the case of the ether? If the ether isn't a material like diamond or PVC or any of these things, where there's literally, an object moving and restoring, and there
Yeah,
isn't literally an object that has mass. So, what would density and stiffness mean for an ether?
good question. And I have three demos later, just a little bit later. But of course, I cannot answer that because that's something, a research question, I guess we could figure out, what would it mean,
Well,
it
I have something we can say at this point. I think even
okay,
though we truly don't know the answer, I agree with that.
right.
But we can say something very general, which allows us to say something without committing ourselves to the unproven.
Okay.
By elasticity, we mean a restoring property,
Yes.
not restoration necessarily of position, but some property which means that that part of the ether is restoring itself in that particular property and thus influencing that property nearby. And
Yes.
then the density would be the inertia of that property. In other words, how difficult is it for that property to be
Hmm.
altered by
Mhm.
the properties nearby? So you can see we don't literally
Yeah,
commit
that's true.
ourselves to it being stiff or massive. We just say, well, it's got a property, the property changes, and this stiffness just tells us how quickly it restores itself when changed, and then the density is
Yeah.
how difficult is it to change it.
Makes sense. And actually, you bring up a good point. It's very risky to just dive into too much detail, right? Some people they go off, oh my God, oh, it's got to be diamond shaped and it's this and it has all these parts. But then you get lost in the details and maybe it doesn't even fit in the big picture. So I think it's good to keep it sort of, as vague as possible while still explaining everything. You know what I mean? So not to get too
Yes.
much into detail. So, well, Einstein's the only one who thought space has properties. And actually, no, there were quite a few people in the past who had the same idea. So this is not some crazy thing. For instance, Lord Kelvin, he thought actually the universe was an elastic solid. And he also said, I never satisfy myself until I can make a mechanical model of a thing. And I really totally feel the same way. If I can make a mechanical model, I can understand it. And he viewed charge as a kind of heat. So we'll talk about charge later. So that's interesting. Of
Hmm.
course, Maxwell, he viewed electric fields as some kind of displacement and magnetic fields as some kind of rotation. And we'll talk a lot about that later too. He also thought that in order to obtain a physical ideas without adopting a physical theory, we must make ourselves familiar with the existence of physical analogies. He viewed electromagnetic wave as mechanical oscillations. And he said, I propose now to examine magnetic phenomena from a mechanical point of view and to determine what tensions in or motions of a medium are capable of producing the mechanical phenomena. So we want to, I'm kind of taking a, starting from that point of view and see with all the knowledge we have today and, with the simulations we can do now, can we do something with that where they didn't have those capabilities, right? Also, Stokes from the Navier-Stokes equations, he thought that the universe is an elastic solid. So he knew that light was a transverse wave. So it was clear to him that space would have to be solid to support shear waves, transverse waves. The thing is, he could not imagine how Earth could move through it, right? A lot of people say, oh, hey, that's crazy. How can you move through a solid, right? That's one of the objections. And so we'll talk about that. I think we have a solution for that.
Yeah.
Of course, otherwise that's what a lot of people stop right there. You can't go. How can you? That's not possible. But it's the wrong question. We are not moving through space like a solid, right? So Newton, he also thought he had lots of ideas, but at one time he also thought that the universe had an elastic ether. He was talking about the elastic force of this medium too. So, and it was clear to him that this elastic force would have to be really large, to have something that we call gravity, which is really interesting. And there are other scientists, just a short list, and of course there are also contemporary people who work on this. So it's not just some crazy thing that one person had. This idea has been coming up. So I think it makes sense to investigate this more and think it through for ourselves. So if we say space has physical qualities, what can we say so far? We have kind of talked about this already. Now we know it must be able to curve, right? We know it can ripple. It can support gravitational waves, for instance. It needs to support transverse waves, shear waves. If you believe in Big Bang theory, then it has to be able to expand. So we know it must be really rigid. What we also can conclude, I think, it cannot be like a gas or a liquid, because if it were a gas or a liquid, it wouldn't be able to support shear waves, right? And curvature. You can't have curvature in a liquid or a gas. So this is important because there are a lot of people working on ideas where they model electromagnetism with a fluid. So if you have a fluid, you run into this problem because, well, then how do you explain transverse wave? How can you get this? It must be rigid, right? How do you get this curvature? So clearly, of course, it doesn't rule out, there's some models it doesn't rule out, but it does definitely have the properties of an elastic solid, and it has an effective wave speed.
Now,
So
why, real quick, what is it about liquids that make it so they can't have a transverse wave?
I think there's one exception, and that's super solids, but that's kind of like a special solid. But, liquids, if you think about the properties of liquids, they're not, the point that they're liquid is that the atoms or the parts, they can move, next to each other. There's no reason that they would stick together.
Oh, they don't shear each other, basic. Like
Yeah,
if one displaces like this, the other doesn't get.
yeah,
Well, doesn't
exactly.
that happen? Isn't there what about viscosity?
Yeah, but
With
it's not
a
perfect. As soon as you have some liquid property, well, you lose some of that rigidity, right?
uh-huh. Yep.
So, right, yeah, I guess if you have viscosity, then it gets complicated, right? If you have viscosity, well, then maybe, yeah, of course, yeah, you could have maybe something that's almost as solid like glass, because glass is a liquid, really. The glass is a
Mhm.
liquid. Um, but it supports, I guess it does support transverse waves. But then, I mean, do we even need that, right? And it makes it complicated. Like, what's the viscosity? And then you have different, you have elasticity and then you have viscosity. So I'm not ruling it out, but
Mhm.
I want to go with the
This
simplest
is this is
model
another
first.
hypothesis that it's not
Yeah,
a
and
liquid because it's
if someone
harder
wants
to
to
get a
run through
liquid.
all this stuff with this idea, go ahead.
Yeah, right.
It's all,
I just bring this up because I already did a video on a fluid model of electromagnetism, and so and in that model, there is a kind of viscous force. It's actually not the same as a viscous force, but it's very similar. Basically,
Mm.
when the charge moves in one part, it drags the nearby ether fluid with it.
Yeah, I wouldn't
So
rule it out, definitely, but it still
yeah,
needs to be, it needs to be such that it has still the properties of an elastic solid, meaning it needs to support transverse waves, right? Shear
yeah,
waves. Yeah. And so also to be again super clear, it's not made of matter. I'm not saying it's composed of atoms or anything like that. You know, some people don't like the word ether at all, so we could just say it's made of space, you know. Um, and actually, it's funny because in physics, a lot of people actually talk about this. They call it the fabric of space-time, even though they say it's abstract, but it's kind of similar, right? Well, we know it can bend and stretch and ripple. Um, the only mental leap you have to do, really, compared to standard physics, is that we're just saying it's actually real. That's the only difference. It's not just abstract, but there is something beneath it that actually has these properties.
it's would you agree that we have to acknowledge that it's an entity? Would you agree with
Yes,
that?
I love your
Yeah,
definition of that. That makes a lot of sense. Yes.
yeah.
And yes, and of course the question is, well, it's got to be four-dimensional. We'll explain all of that. Now, you brought up one question, like what is it, if you're saying maybe what are the parts if there are no parts? So I have a few simulations. One of them is maybe it is some kind of, it could, in theory, right? I don't know. Philosophically, maybe it's not possible, but in theory, it could be continuous as far as we know. I mean, maybe deep down, it could even be way below the Planck length. Like we don't know for sure, right? It could be deep down. It has a granular structure, but from what all we know, it might just be continuous because we can't really do any experiments right now, at least probably not yet, to detect like how small is that smallest part.
Yeah. Yeah,
And
Henry gave me a really good argument that it had to be discrete.
okay,
But if you make a continuous model, then that's fine because that simply such a model just presumes that if there is discreteness, then it's just too small to be detected. And that's fine because maybe and there all the indications are is that that discreteness can't be detected yet. Is that
exactly. And
it's at
once we
our
do,
scale that we're aware of, it
yeah,
basically is
yeah, yeah.
continuous.
Once we do, of course, then we can adapt it because the problem is if we already say, because I know some people say, oh, it's got to be FCC crystal, right? I know some people that think that. The thing is, if you put the whole model onto this and then it doesn't work out, then again, I don't know, where do you start again, right? You have made all these assumptions, maybe you determine
Yeah.
certain properties of who knows electrons based on that, right? And it's sad because then maybe it doesn't have to be necessarily an FCC. It could be. I mean, I know, of course, people who work in material science who think it has this crystal structure. And also Hagen Kleiner, too, worked on this initially. He thought of the universe more like as a crystal. And of course, it looks cool and, it helps to model it, right?
Hmm.
Um, I know someone who also thinks it has this diamond-shaped structure.
Hmm.
Yeah, I mean, could be. I don't know. I mean, it's it's all, the thing is in all these models, you end up with the same wave function. Like transverse waves, you can very easily abstract it to describe. Once you get a little bit away from that level at that order of magnitude, it doesn't really make a difference, because you're not gonna model everything based on these little the parts. You could never do that, right? It's way too computationally intensive. And the important thing is, what scales are we talking about? Now imagine it was an FCC crystal, okay? Imagine we have this little component here. If this were Planck size, most people think it's probably around Planck length, right? How big is an electron? If this were Planck length, like this one little golden sphere, Planck is 10 to the minus 35 approximately. So if this were a grain of sand, even so, this gold thing, a tiny grain of sand, an electron, okay, would be the size of the Milky Way. I mean, that's the
Hmm.
scale we're talking about. I mean, I'm talking about Compton length, right? Compton length. So,
Yeah.
I mean, that's like it's 100,000 light years or something like that. Huge number. You're not gonna anyone who models galaxies, for instance, they're not gonna model at the size of grains of sand, right? they're going to model,
Yeah.
I mean, a solar masses maybe. I mean, so the point is, it doesn't matter. It might, who knows what it is? It might be bubbles.
Well,
I don't know.
it might matter, but then you'd have to come up with some kind of prediction where the granularity of your model gave rise to some new phenomena, and
Yeah,
then
it
you
could be,
actually
right?
observe that
Yeah,
phenomena, and
maybe,
then
yeah.
fantastic. But until that happens, I don't think we should proceed on such a hypothesis because
We should stay
it's just
open, right? We should, I think at
yeah, of
each step we
course.
need to be clear. It will work whether it's continuous or FCC or diamond. It doesn't matter right now yet. Maybe later if we come up with something quarks, I don't know, maybe it matters. But
Uh-huh.
right now, I don't think we should, decide, right? There's no reason either way.
Right.
Now, of course, in the simulations, because I'm working with computer simulations, of course, I have to draw something because otherwise we can't see anything. So I might be using springs and I might be using, green squares. It doesn't mean I think that's what it is, but when you want to visualize something, you need something to see. So, and obviously, grids are just made for computers. That's why I use it. That doesn't mean I think it has their little springs. Okay, just to be
Uh-huh.
clear on that.
Another question, like on this same topic, the parts of your media, they're moving with respect to the other parts. Are you committed to the idea, at least in this hypothesis, are you committed to the idea that the changing property of the medium is an alteration of its location?
Oh, that's very philosophical. I don't know, to be honest. I mean, I
So
think
we should take the deformations that we see here to be representative of the change of some kind of property. We know not what property
oh,
of the
yeah.
medium.
Yeah, I mean, of course, in the simulation, we kind like when we do a computer simulation, we have our absolute container, the computer, and inside I have that visual, right? So, of course, I don't know, is space the same way? Is there something in space or is it space itself? And I don't know. I couldn't answer that. I wouldn't know how we should
Right. Yeah,
prove
I mean
this either
that's
way or the other. So,
yeah.
but
So
again,
we
as a
should
concept,
take
yeah, go ahead.
so as I move forward with your simulations, I'll take these visualizations, the changing of position of all these white balls or the changing position of these green cubes. I'll take that to be a analogy for the changing property of the medium, whatever that property might be.
Yes.
We can just say, what property? Is it the temperature of each location? Is it the position of each? I don't know. It's a property.
Yeah,
That's
yeah.
it.
Of course.
It's some property that changes.
Yeah,
That's
yeah.
all we know so far.
Yes. I'm using, of course, location just because we are
Because you can
talking about,
visualize it.
yeah, the displacement. But of course, you could use something else. But I think the displacement is probably the easiest,
Yeah.
yeah. Now, briefly, I know this table is a bit premature because we haven't talked about anything yet, really. So don't look too closely, because there's always a question. Well, could it be something else, right? Now we've talked about if space has no properties. I think we can rule that out because there's no explanation for anything. We cannot explain anything at all. There's no mechanical model whatsoever. Now, superfluids, people talk about this, and the problem there is, as I mentioned, that there's no shear. We don't have any shear waves, so that's a problem there. Um, Now, the elastic solids, this is the model we're going to go forward with, and of course, it could possibly be like a super solid or something that's almost a solid and has some viscosity, maybe. There are some other models, like it could be a liquid crystal, and there's some other issues with that because liquid crystals, they don't really have shear. They don't have a fixed speed of the wave, and also it's so all of these have some issues when you model certain things. And the reason I'm mentioning this, it doesn't just have to work for, say, gravity, right? It has to work also for spin 1/2, and it has to work for charge, and it has to work for special relativity. All the pieces have to fit together. So if someone, there are good models, for instance, for liquid crystals for charge. That works really great, but how about then, how do you explain then, general relativity when you have that model? So that's why it's so difficult because you have to cover
Yeah.
everything basically. So yeah, so basically to answer the question, does space have properties? I think it makes sense to say yes, space does have properties. I think it has the properties of an elastic solid, which would explain that it can support different kinds of waves, that it can curve and expand. Now, and that's literally the only mental thing you have to do, if you can accept the idea that space maybe has properties, that's the biggest leap really for the whole series. Once you are able to say maybe let's at least consider it, everything else follows from that. So even if you are convinced that no, space can't have properties, it can't hurt to think about it, right? So maybe we can see how far we can take this. Is there any roadblock later on? Um, yeah, and that's what we're going to explore in the next couple of episodes. So the question basically is, well, if space really has properties, well, what does it mean? Does it imply for general relativity? Can we explain anything then? What about special relativity? So this ends our first episode.